Hello, my name's Alan, and I'll be presenting on Narcan, Chem 263, Spring 2025. Unfortunately, according to the CDC, we can see that fentanyl, a synthetic opioid, is the leading causes of overdoses for Americans. From this graph, we can see all the other drugs that have been used by Americans, but we can specifically see that synthetic opioids are the leading causes of death by a large degree, as we see from 2016 to 2022, where it skyrockets. Fortunately, we have Narcan to combat the increase in overdoses we see in America. Naloxone is the official name, but it is commonly known as Narcan. It is a life-saving drug that rapidly reverses opioid overdoses. It was first made in 1961 by Jack Fishman and his partner Moses. It is currently widely available at local drugstores now. This presentation will be going over three key points. The first point is how Narcan interacts with the human body, specifically how it can reverse opioid overdoses. Which brings us to the second point. How can Narcan's structure do that? And we will explore that in depth, and we will see how it is made, how Narcan is made. On the left, we can see the keys and the flags. So anyway, if you look up to your top left of the screen on any slides after this, you'll see which section we will be in. We'll be in is body interactions. Narcan is usually administered via nasal spray. This nasal spray allows it to rapidly diffuse through the olfactory nerve and straight towards the brain, which is its target area. There are two primary pathways that Naloxone enters the brain. The first one, as mentioned, is from the olfactory nerve. The second one is from the trigeminal nerve, which is around the entirety of your mouth and your nose. There's a minor pathway, and it is through the system circulation, but since it circulates throughout the body, it is less effective in delivering an effective amount to the brain. As mentioned before, also, Naloxone quickly diffuses through lipid layers. Since they're highly soluble in lipid layers, this allows it to go through the blood-brain barriers rapidly. But of course, certain interactions and certain conditions can hamper the delivery of Naloxone to the brain. Once Naloxone reaches the brain, we can see that the initial conditions has fentanyl on the receptors. And Naloxone is an extremely competitive antagonist, meaning it will rapidly displace fentanyl molecules from the mu receptors. How does Naloxone outcompete fentanyl? Naloxone has a higher affinity for mu receptors. These mu receptors are also known as opioid receptors. These receptors exhibit a certain biological effect. For example, too much fentanyl, you will overdose and die. But with Naloxone, since it is an antagonist, it will not exhibit these cascades of effects. Why? Well, as we see in the next couple of slides, certain parts of Naloxone's structure will basically prevent it from triggering this receptor. Section, which is chemical properties. Naloxone structural properties include a melting point of 178 Celsius. It also has a water solubility of 5.64 milligrams per milliliters. This is relatively low, so its water solubility is not that great. But that also means that it's highly lipid soluble, which brings back to the fact that it is able to diffuse through those nerves and to the brain through the blood-brain barrier. Here, it also has a pKa of 7.94, and this is specifically to the OH on the benzene ring, the ring with the internal circle there. It also has a molecular weight of 327.4 grams per mole. Here we'll be going over structural properties. The first group that is being circled right now is phenyl. This is the entirety structure of phenyl. The second group being circled is ether. Although it's just circulating the oxygen, it also includes the carbons that are bonded to the oxygen. The same thing can be said for ketone, because it's just circling the carbonyl of it. It also includes the carbons bonded to the carbon that is double bonded to the oxygen, so the entirety of this group. The fourth group is the nitrogen heterocyclic ring. It's basically a ring with a nitrogen replacing one of the carbons of the ring. This is the entirety of this group, and it is facing towards or out of the screen. The fifth group is the nitrogen allele, or this alkene right down here that is separated by sp3 carbon. This specific part right here, or the nitrogen allele, is what gives it its antagonist properties. It's because of steric hindrance, prevents Naloxone from completely interacting with the mu receptor. This prevents the triggering of the cascade and certain bodily effects. The sixth group is in alcohol, and it's just right here. Here we'll be identifying the different regions in an infrared graph with the different functional groups of Naloxone. The first one that is being circled is the OH bond, which is typically around 3600 to 3200, but here we can see it's around the upper end of 3600 to around 3300, but it's hard to determine since OH bonds in IR graphs are typically broad. But this specific part of the graph can either come from the alcohol or the phenol. The second region that is being circled is the sp2ch bonds, which can come from the benzene ring, and is typically around 3100. The third one that is being circled is the sp3ch bonds, which can be found between the nitrogen and the alkene, since it's separated by that, or any other single bond. The fourth group that has been circled is the carbonyl, or the ketone. This is specifically the C double bond to O. And ketones are specifically around 1750. The fourth group that has been circled is the alkene, the C double bond to C. It's typically around 1640 or 1650, typically around that small range. The fifth group that is being circled is benzene, which is either can show up in two places, 1600 or 1500. And the sixth group that is being circled is the ether C single bond to O, which is typically around 1050 to 1250. Here is H1 and C13 NMR data of Naloxone. Top graph is H1 NMR, and the bottom one is C13 NMR. There are a total of 14 signals on H1 NMR, 2 of which are proton exchangers, which basically come from the alcohol or the phenol. The other 12 are all protons that are non-equivalent sets with varying splitting patterns. C13 NMR has a total of 19 signals, and each one of them are non-equivalent sets. And here we reach the similarities between fentanyl and Naloxone. The first similarity between them is the nitrogen heterocyclic ring, which both of them have it. The second similarity is the aromatic ring, which is seen both present on the top left of their respective structure. The third similarity between them are the C double bond to O's, or the carbonyls. And that is where the similarities between them end. Here are the key differences between fentanyl and Naloxone. The first key difference is that fentanyl's heterocyclic ring is also called the piperidine ring, which is different from Naloxone's heterocyclic ring, which has a different name. The second key difference is that fentanyl has an MI group, which Naloxone does not have. The third major difference is that Naloxone has these fused rings, which is called the perhydrophenanthrin, which fentanyl does not have. Another key difference is that Naloxone has the alkene, and it also has a ketone, which is different from the fentanylamide group. Another key difference is that Naloxone has OHs, phenol, and an alcohol. The last key difference is that fentanyl does not have an ether, while Naloxone does. Our last major section, the chemical synthesis of Naloxone. Naloxone is synthesized from oxymorphone, and oxymorphone can be synthesized from naturally occurring opiates found in the wild. Once oxymorphone has been produced, it would then be converted into noroxymorphone, which is then turned into Naloxone. And we will be going over the specific steps in the next slide. Here, oxymorphone will first undergo acetic anhydride reflux, then BRCN with heat, and an acidic workup with heat. This will convert it to noroxymorphone. Once there, an SN2 reaction will occur with BrCH3CHCH to Naloxone. The first reaction with oxymorphone is the acetic anhydride reflux. This will protect certain groups, like the alcohol and phenol, and prevent it from further side reactions later on in the process. Here we have the OH group on the benzene, specifically the lone pair on the oxygen, attacking the carbonyl. Why is it attacking the carbonyls? It is because it is electrophilic, and this is due to the adjacent carbons withdrawing electron density from it, making it electrophilic. And from this attack, we can see the pi bond between the C double bond to O break and go towards the oxygen. This will form in O minus and in O plus, which is terrible because if the O minus will collapse, it will kick off our original H and reform the original reactant, which we do not want. And this is where a lone pair on water will deprotonate the OH plus, which will form the third structure. Once there, the O minus can collapse, and although there is a chance that it will kick off our original group and recreate the original reactant, the reaction will proceed in which the O minus will collapse and kick off the other group, forming a carboxylate. This will produce the fourth structure, which is then repeated once more with the alcohol, which creates this structure, which basically has an ester bond. This will protect it from any side reactions. Reaction with BRCN is called the bond-run demethylation, which will replace the methyl with a nitro group. And here is the mechanism. The lone pair on nitrogen will attack the electrophilic C, which is triple bonded to the nitrogen, which will then break its bond with Br, and the electrons will go towards the Br. This will produce our second structure, which then we have a protonated nitrogen, which makes it susceptible to an SN2 reaction, since Br is a good nucleophile, and protonated amines are somewhat a good leaving group, and this will allow Br to grab that methyl to demethylate it, and this will produce our third structure. The final reaction from oxymorphone to noroxymorphone. This is an acid workup at elevated temperature. The reason why is because it is removing the protecting groups, and it will hydrolyze the nitrile into a carboxylic acid. But this structure will be a carbonamate, which will then decarboxylate, forming noroxymorphone. The first part of this mechanism is the protonation of the carbonyl oxygen. Using its lone pair, it will grab an H from HCl, breaking the bond between H and Cl towards the Cl. This will form our second structure, the protonated oxygen, which will now pull more electron density from the carbonyl C, making it more electrophilic. This is because it will try to satisfy the positive plus charge. This will allow the lone pair on oxygen of water to attack the carbon of C. This will then form the third structure to the right, which will include a protonated oxygen from the water attacking. This will be deprotonated by a weak base, or specifically Cl-. This will produce our fourth structure, which we want to remove this diol group now, by protonating the O to the benzene ring with an H from HCl. This will produce our fifth structure, which then allows OH plus to be a good leaving group. So a OH will collapse and push off this group, forming our original OHs. This step will be repeated for the alcohol. Now the nitrile group will turn into carboxylic acid. This is done by the nitrogen lone pair first grabbing an H from HCl, which produces our second structure, in which now the C triple bond to N will be even more electrophilic since now we have a protonated amine. This will make it more susceptible to the lone pair on oxygen of water to attack it. This will produce our third structure, which then produces a protonated oxygen, which is deprotonated by Cl-. This will prevent nitrogen from collapsing and kicking off the OH2+, since OH2+ is a better leaving group. We'll produce the fourth structure to the very right of the screen. Here, nitrogen is using its lone pair to protonate one more time. This will produce the next structure, which makes the C double bond to N more electrophilic since N is protonated and is withdrawn more electrons to satisfy that plus charge. So a lone pair on oxygen will collapse that. It produces the next structure, which is similar to other structures from previous slides. And we see this carbonyl will be more electrophilic since it has an oxygen with a plus charge. This will allow the lone pair on oxygen on water that will attack the electrophilic carbon, forming the next structure. This structure is then deprotonated by a weak base. This will prevent the lone pair on nitrogen from collapsing and producing previous structures. This will produce the next one, and nitrogen will be protonated one last time. This will allow it to be a better leaving group, which we can see in the next leaving group will be removed as the lone pair on oxygen collapses. And here we can see the beginning of this structure right here, which is then deprotonated. Once deprotonated, we have this structure, the very last structure on the screen. Here, a carbamate is formed. This carbamate is extremely unstable, the specific structure right here, and will decarboxylate. Specifically, the lone pair on nitrogen will first protonate, forming the next structure, and this structure will then decarboxylate, forming neuroxymorphine. The final reaction to form naloxone. Here we have an SN2 reaction where the lone pair on nitrogen will attack the allylic bromine carbene. This is a SN2 reaction and it is concerted, so it's one step. It will then form the second structure, which is ammonium, since it is protonated amine. A Br will deprotonate it to form our naloxone. This is our final product. Slide. We know that Naloxone can help us reverse opioid overdoses, and this is because of its special properties of its functional groups. But we don't really know all of its properties. We still need more research on how different parts of Naloxone can contribute to its antagonist properties and how it also contributes to its competitiveness with mu receptors. Another study should be done to determine the long-term effects of Naloxone usage. Although we know that it saves lives, but we don't know the long-term effect it has on a person's health. And I thank you today for listening to my presentation.